Hello everyone. So my talk today is the sixth part of a series of webinars on boundary systems organized by the Boundary System Task Team of the Ocean Observing Physics and Climate Panel. And this time I will be talking about the Mediterranean system, and I will be focusing on the observational side, while my colleague Paolo Odo will talk about modeling of the system in a companion talk. So my name is Anthony Bosse, and I'm a researcher at the Mediterranean Institute of Oceanography in Marseille, in France. And I'm working closely with observations in the northwestern Mediterranean Sea. So if we look at the Mediterranean Sea from space, we can define different regions according to how the chlorophyll and the primary production works. And if we observe the different patterns, we can see that the Mediterranean Sea is strongly constrained by horizontal currents, its physics, boundary currents and eddies, but also quite a lot by the vertical dynamics that happens in different basins. And we have in the Mediterranean Sea areas of deep convections, like the Gulf of Lion in the northwestern Mediterranean Sea, that occurs in this area and produce a strong bloom in the spring. So in this area, it is quite important to know how things work. So if we look a bit closer to the western Mediterranean Sea, this is the circulation patterns. We have the inflow of Atlantic water from Gibraltar that flows along the Aegean coast and produce lots of mesoscale eddies. And in the north coast, we have the convergence of the circulations of Atlantic water on the slope and the circulation of warm and salty intermediate water that comes from the eastern Mediterranean Sea and flow along Sardinia and Corsica, and then finally flow along the northern boundary of the basin, which forms the Northern Current. So this current system is very important in this area because it drives the cyclonic circulation at the basin scale. That circulation is closed further south by a front that is called the North Balearic Front, the NBF on the map. And as I said, it drives in the center, the cyclonic circulation drive an isopycnal doming in the center of the basin. And that leads to a strong preconditioning to deep convection. So the horizontal circulation is very important to make the convection possible in this area. And in winter, when we have very strong heat loss at the surface of the sea, we can have heat loss up to 500 watt per square meter or even higher on very strong episodes of very dry winds. We can trigger some very intense vertical mixing, and we regularly observe mixer depths down to 500 to sometimes even to the bottom at 2,500 meter depths. And this deep convection has a strong impact on the phytoplankton, as you can see on the satellite images. The phytoplankton is completely diluted during those episodes, and it brings concentrations to very low value. And if you observe by satellite, you can then guess where the deep convection is happening. So this image is from February. And what happens after the deep convection is there's a strong bloom event that occurs usually in April. And here you have an image of a very nice example in 2013. After very strong convection events, the bloom was also very intense and very big. And so yes, that links to my first slide where I was describing the spring by a region of the northwestern Mediterranean Sea. So it's basically how it works. And you can see that the system is organized in many different scales. On these satellite images, you could see lots of eddies, lots of fronts, lots of currents, lots of very fine scale structures. And everything is evolving quite fast at the seasonal scale, and also evolving at decadal trends impacted by climate change. So that really brings the need to have an observing system in this area that can actually monitor processes from hours to decades. So to be able to resolve the dynamics of the meso and the sub-meso scale, and also to monitor the changes on a longer time scale. So this vision was started in 2010 when the MOOS, MOOS stands for Mediterranean Observing System for the Environment, and it was created in 2010 by the French scientists to establish a multi-platform integrated observing system for the long-term monitoring of the North-Southern Mediterranean Sea. So the idea was to combine platforms, to have time series, moored time series under the sea, fixed time series on the shore to measure atmospheric deposition, for instance, for the coupling with terrestrial inputs, and combine lots of different platforms in the sea, like autonomous gliders, autonomous profiling floats, and ships. And everything, the idea was that everything could fill the gaps between the different scales that every platform can resolve. The mooring has a very high resolution in terms of temporal resolution, but doesn't cover a large area. And a ship can cover a large area, but doesn't stay very long in the water. So the integrated approach was made to fill all those gaps. So since 2010, we have this network that that focuses, as you can see on the map. There is a few moorings. So the Lyon mooring that's located at the deep convection area, Antares and Difamed, and so they're all parts of the EMSO-ERIC infrastructure. And those moorings are maintained since about 2007 for some, and continuously, like every year, they're maintained during the MOOS cruise that we have every summer. We also have a few moorings that are a bit shallower on the shelf, and we also have autonomous platforms. So the gliders, they work mostly along two lines. This is along the two red lines you can see between France and Corsica, and between France and Menorca. So those two lines, they're meant to be repeated several times a year to provide as many data as possible. And we also help to deploy Argo floats to maintain a good number of Argo floats in the area, to maintain the processes we want to monitor. And this is something we do on the MOOS cruise usually. We even recover some floats so we can recycle them. And as I say, in the end, we also have cruises. So every year we go for a basin scale cruise. This is all the blue dots you can see. They cover most of the basin from the north to the south and the east to the west, with long transect crossing the basins. And finally, we have some HF radar sites. So we have two HF radars that's integrated with different European projects. And so they work, one is working south of Toulon, so that's the one west on the map. And then the other one is operated near Nice. And this one is more recent, has been in operation since 1 or 2 years. So yeah, if we look at the convection first, the Lyon mooring has been allow us to describe with lots of details the convection episodes, and in particular during an intense period of deep convection from 2009 to 2013. There's been a very intense deep convection with mixing down to 2,500 meters every year. And so the mooring was really established before that period. So we had lots of winters with convections. And what we observed after those 5 years was actually a strong difference, a rapid change in the deep convection that happened around 2014, where the convection was much shallower, and we started to see a very strong increase in temperature and salinity of the intermediate depths. And as you can see on those graphs, the temperature and salinity observed in different boxes from this integrated system So it brings you insight to what's happening, where those signals are coming from, and what are the amplitude. And as you can see, the salinity and temperature increased by almost half a degree quite rapidly in 2014. And after, that's also happened in a time where the convection is much less intense. So the heat content and the salt content of the water column in this area has really increased. And we can expect next time that there will be very strong deep convection event, that the deep water are going to be changed quite a lot. Now, if we look at the autonomous platform like the gliders, you can see that there's been a very strong effort to deploy gliders since actually even more than before 2010. There was already some glider deployment, so it's been almost 15 years of deployments now. And yes, as I say, we focus in MOOS really to deploy gliders along two lines. So the line between France and Corsica, and the line between France and Menorca, T02 and T00. And yes, so the objective is to have about 4 to 6 months of glider data, and to really try to have data during the winter and during the spring when we have the bloom. So if we merge all the data, the glider data that give us some indications on the circulation, we already have a picture of the horizontal circulation with the main features. You can see the northern current that flows along the continental slope in the north, and some recirculation in the south with the North Balearic front and the west Corsica current. It's also interesting to look at the seasonality of the signal of the currents. Here you see that the winter, the currents are much stronger than during the summer. Those two maps show surface currents and also currents at 300 meters, so it's a bit intermediate depths, whereas less intense current. And along those glider lines, we can reconstruct the climatology or mean state of the temperature and salinity at different places. So this is 4 sections from the east to the west of the northern current, from Nice all the way to Perpignan, so from the Italian coast to the Spanish coast, basically. And we can describe the transport of different water masses there, and the northern currents there flow with the transport of about 1 to 1.5 Ferdrup for the upper 200 meters, which is numbers that have been described before, mostly by using CTD cast and assuming that there's a level of no motion at some depths, and with a few ADCP sections. So here with the gliders, we've covered a lot more different situations with lots of sections during the winters and during the summer. So we have a better view than when we just use the ship. So, and what we can do with those data is, when we want to look more at processes that happens along the boundary currents, we can look at, for instance, the effects of downtront winds. So how winds interact with fronts and with currents. And so actually, when the wind blows in the direction of a geostrophic jet, that the Ekman transport can drive some mixing, can enhance fronts and drive turbulence. So this is the work that that we've done to characterize the effect of fronts of winds along the northern current front. And here you have an example of the sections that cross the northern current near the Gulf of Lion during a very strong wind event, a strong northerly Mistral event. So it's typical wind that blows from the northwest. And as you can see in the western part of the Gulf of Lion, this wind is actually aligned with the current. So the downfield wind can push the Ekman transport, can push the dense water on the light water and steepen the fronts. So it's here represented by those lines where you can see that the heat fluxes is reaching 1,000 watt per square meter, while we have an equivalent heat flux generated by Ekman transport that can actually be even stronger. So this system is very coupled with what happened in the wind, especially during the winter, when you can really have a strong coupling, and Ekman transport or Ekman effects, mechanical effects of the wind, can actually be of very strong importance compared to the heat loss. And yes, we can also go a bit further in the details, but basically, if we compute potential vorticity diagnostic along the currents, we can quantify the effect of some instabilities. And here we could highlight that during those events, the slope current was unstable in the upper part, as you can see here with the negative potential vorticity patch. And that brings some interesting questions, because if we look at cross sections of the current and we look at other variables like dissolved oxygen, chlorophyll A, you can see that during those instability periods, the front generates a lot of secondary circulations that bring some particles, some carbon down below the mixed layer depth. So there's a mechanism to subduct material and to bring down oxygen and nutrients. And those fluxes, those vertical fluxes, are not very well understood yet. So it's an interesting thing that you can study when you establish a long-term monitoring system, and then you actually are able to study also very fine-scale processes, because some platforms cover a very wide range of scales. So now, if we look at the Northern Current and its interaction with the slope, because the Gulf of Lion is there's a shallow shelf of about 150 meter deep and 100 or 200 kilometer wide, and that shelf sometimes is influenced by Northern Current intrusions on the shelf. And so to monitor these intrusions, a mooring has been established on the continental slope here, as you can see on the map. So it's basically off Marseille at the beginning of the continental shelf. There's an ADCP that is moored at the bottom on the 100-meter isobars, and it measures when the Northern Current go on the shelf. And it's also located next to the future SWOT SWOT track. So it would be interesting to look at this intrusion during the SWOT launch. So, and some mechanism of interactions of the wind again and the current could be done to see how the Northern Current can actually intrude on the shelf. And this happened during different type of winds. So it's either easterly winds that push the water on the coast and push the intrusion, brings the intrusions straight on the shelf, or some Mistral events, so more northern winds that will generate some upwelling, and then after the relaxation of the upwelling, then the intrusion can happen. So yes, and now this mooring site has been used to train algorithm to trying to detect from satellite when the intrusions can happen. So a study has been done here, as you can see, to study these intrusions and to link it with the satellite measurements, with a nice perspective to use that during the SWOT altimetry period again. So SWOT will be a satellite that will measure SSH along a wide swath. So it will take like 150 kilometer wide at once, and we'll be able to resolve some mesoscale features, and we bring a lot of new information on the surface circulation. So yes, and now a few words about the another aspect of the observing system we have here is the HF radars. So HF radars, I said, just south of Toulon. So here, as you can see on the map, it's located just before the Gulf of Lion shelf, and Those HF radars have been operated since 2010. So it's a big data set now that's available online. And as you can see, it resolves scales from, again, from sub-inertial periods to internal. So with all the data we have, we can see how the signal of the Northern Currents evolve at very short scale or at seasonal to interannual scales. And as we have all these platforms working together, we can also compare them. And you can see that the radar here can compare well with geostrophic currents measured by gliders just under the radar. And here on the right, you can see that the radar can also be compared with ship ADCP and bring some good confidence that the radar is measuring good intensities of currents and good directions. So yeah, lots of effort has been put on the HF radar side to process to the data processing, and now there is a full chain of processing of the data that's running, and that allows to fill gaps. So using EOFs, it fills gaps that can happen in HF radars when sometimes there are some technical problems. And now the HF radar can be used to study the mesoscale variability of the Northern Current. And it's been shown that the Northern Current can generate lots of eddies and mesoscale features that are formed either on the northern flank or the southern flank of the Northern Current, and can be detected by these HF radars. Okay, so to conclude, so we have now, I'll just say a word of the status of the Northern Western Mediterranean observing system. So it's involving quite a lot of people in France, different labs, and also with close international collaborations. And it's now quite mature with more than 10 years of data that has been collected, and already in important academic valorizations. But yeah, everything has happened because because I think there was a strong governmental support, and those long time series can only survive if there is a vision on the long-term funding of this time series. Otherwise, there's always a risk of gaps in data coverage. So at the moment, we still have a few years of funding for the MOOS, and then every 5 years we can renew that funding if we show that we're doing things like we should do. And yes, some perspective to this, we can think that this observing system could be in the future will probably be more integrated into European or even global research infrastructures. And so some of the components of the infrastructure, like the gliders or the Argo floats, or the biogeochemistry, the carbon, is already part of some big consortiums or infrastructures like EuroGOOS, EuroArgo, Ocean Gliders and Groom for gliders, and EMSO for the moorings. So in future, we can also anticipate that there will be more parameters measured. So we're already trying to work on new sensors to integrate to our platforms, like CO2 measurements on moorings or CO2 measurements on gliders, and imaging also, genomics from the cruises. So we have lots of testing new parameters to try to integrate to this long-term time series. Although it takes time to validate those time series first. And then also another perspective is to use new methods like deep learning algorithm. So here's an example where the CanyonMed algorithm has been used to train on a database to reconstruct the carbonate system, only from temperature and salinity and oxygen profiles. And there has been also some more work on this deep learning methods on the HF radar side, actually, to reconstruct the geostrophic part and geostrophic components. And to conclude, we can say that, yeah, a better synergy with modeling community, or just like more closely, more synergy, I guess, is always good. And with operational products could also be beneficial to the observing system. Okay, so this was my talk, and so I now invite you to join us on the 4th of May for the interactive discussions, and I hope you enjoy the talk.